Okay, this is Physics 112, Lecture 20. I'm going to talk about capacitors in parallel. Capacitors in parallel. And the main thing is we want to find equivalent capacitance. That's what we want to learn. Okay? Now, when I talk about capacitors in series, what I explained to you was that first, imagine you have a capacitor, a parallel plate capacitor. The charges on these plates are one is positive Q, then there's negative Q. The capacitance, we call it C1, and the potential difference between these plates, V1. Then this wire coming out from the negative plate of this capacitor now goes and joins the positive plate of the next capacitor. And so this is negative Q, then it will be positive Q, there will be negative Q. The capacitance will be C2, and the potential difference will be V2, and so on. So if you put capacitors in this fashion, then we call it capacitors in series. All right? Notice that the Q's are the same here. Now, the voltage drop is that when you add V1 and V2, then you'll get the total voltage drop from here to here. That's what we did. And if you do not remember, please review lecture number 19. Now, I'm going to put capacitors in parallel. What I mean is like this. First, I'll have a capacitor, and the charges will be Q1 and negative Q1 here. The capacitors, will call it C1, and the voltage difference between these two plates will be V. Now, then it will go on to another capacitor and join like this. And the charges on these plates will be Q2, negative Q2, and it will be C2. But this wire, this line, if you follow the wire here, it's the same point here, right? So this point and this point, they meet here, and they have the same potential. Similarly for this point and this point, so then the potential difference between these two plates is the same as potential difference between these two plates. So it will also be V. Okay? And so I can keep on going. So let me draw one more. Then until I get to my battery, so positive and negative node, and then I have my battery here. Connected to that. This is positive, this is negative. And the potential difference between these two nodes will be V. So this will be C3, this will be Q3, this is negative Q3. Right? So the potential difference between these two plates, these two plates, these two plates, they are all the same. It will be V. What's different is the charges are different, Q1, Q2, and Q3. Of course, the capacitance are different, C1, C2, and C3. So we know the general formula for a capacitance. For one capacitor, that is C is equal to Q by V. So Q is equal to CV. All right. Now, unlike the capacitors in series, the charges on these plates are different. So the total charge of this is Q1 plus Q2 plus Q3 will be equal to Q. So we know Q is equal to Q1 plus Q2 plus Q3. Okay. Now we just use this simple formula. Q is equal to CV. So Q is equal to Q1 is C1 V1, but V is all the same for all of them. So C1 V plus Q2 is C2 V plus Q3 is C3 V. So I can pull out V as a common factor. I get C1 plus C2 plus C3 times V. So that's what I get. So then if I compare with this formula, then this equation looks like it is like Q is equal to some C times V, but where this C will be your equivalent, C equivalent, right? So this C will be C equivalent. So our formula for equivalent C, equivalent capacitance for capacitors in parallel will be C1 plus C2 plus C3. So it's easier, not like the business of like capacitors in series. You don't have to do 1 by C is equal to 1 by C2 plus 1 by C1 plus 1 by C2 and so on. All right? So that is very simple. And actually what it means is that this formula, Q is equal to C equivalent times V, then what it means is there is only one capacitor representing all these. This is my battery. In the future we'll just write battery with 2 lines, but right now I'm drawing all the nodes and stuff like that. So this is positive, this is negative, this is C equivalent, this is Q, total Q, and this is total Q, right? Q is equal to CV, so that will be negative V. So the effect of having these 3 capacitors in parallel like this is the same as having one capacitor like this, right? And the voltage difference between these 2 nodes is V. So when you have that, then in order to find that equivalent capacitance, you just add them up. So let me do an example. An example will be, let's call it page 2. Let me do a simple one. So let me draw capacitor C1 and then another capacitor C2, and they are in parallel when I draw like that. Okay, so now what is the equivalent capacitance of this? Well, equivalent capacitance for this will be C is equal to C1 plus C2. Very simple. So if I have 2 guys in parallel, all I have to do is add them up. I get the equivalent capacitance. So if I have 3 of them, then I add 1 more, and so on. The only thing tricky about capacitors in parallel is this. Sometimes you do not know or you do not notice that they are in parallel because of the figure. For example, let's suppose I have a wire, right? Like that, something like this. So are they parallel in series? Well, the thing is that because this is the same wire continuously going like that, it is equivalent to something like this. Right? Because you just fold this wire up here, it will be like this. So this is capacitors in series. All right? So what about something like this? Well, in this case, you have to know that this and this, as we explained before, this and this will be in series, this and this will be in series. Then after that, the resulting one will be parallel. Then what it means is, if I have C1 here, C2 here, C3 here, C4 here, first it is having one guy that is the equivalent capacitance between C1 and 2. Let's call it C1, 2. And let's call this C3, 4 because that's the equivalent capacitance for 3 and 4. So I have C3, 4 like that. So that's C3, 4. So then C1, 2 and C3, 4 will be in parallel. Okay? So this and this in series, this and this in series, this and this will be in parallel. So you have to calculate two steps. First, I have to calculate C1, C2 in series, C3, C4 in series. Then after I get the answers, then I have to make them parallel, calculate the equivalence capacitance. So let me do an example of this. Let's suppose in this capacitor, the one that I have drawn here, this odd-shaped picture, C1 is equal to 2 microfarad, C2 is equal to 2 microfarad. Okay, and C3 is equal to 3 microfarad, and C4 is also equal to 3 microfarad. So, this one and this one, they are in series. So I have to calculate equivalent capacitance C1, 2. I'm calculating this one because that's the equivalent capacitance for C1 and C2 in series. C1, 2 is equal to 1 by C1 plus 1 by C2. That's what we had learned in lecture 19. And so C1 is 2 microfarad, C2 is 2 microfarad, so 1/2 plus 1/2, it will be 1. So then C1, 2 will be 1 microfarad. Okay? Similarly, C3, 4, that is this one, is the equivalent capacitance for this plus this in series. C3, 4, according to our formula, will be C3, 1 by C3 plus 1 by C4, because they are in series. And both of them are 1/3, 1/3. If I add them up, it will be 2/3. So then C3, 4, don't forget you have to flip that. So then I get 3 by 2 microfarad. So now I get C1, 2 and C3, 4. So now I want to get the final equivalent capacitance. Then in that case, the final one is C1, 2 and C3, 4 will be equal to C1, 2 plus C3, 4. Why is that? Because C1, 2 and C3, 4 are in parallel. So according to our formula, we have to just add them up. So C1, 2 is 1 and C3, 4 is 3 by 2. So then C1, 2, 3, 4, the whole equivalent capacitance for the whole arrangement is 1 plus 3 by 2, so that's 5 by 2 microfarad, or 2.5 microfarad. Alright, so it'll be 2.5 microfarad. C12 plus C34. C12 is 1, C34 is 3 by 2. So I add them up, I get 2.5 microfarad. That is a C1234, which is the equivalent capacitance for the whole arrangement. Okay? All right.